Right.
Okay, so next speaker is Xiang Li from Tsinghua University, and he's an associate professor with the Department of Automation, and he received the highly commended paper award in 2013 IF Tom, the best paper in robotic control in 2017 ICRA, and the best application paper finalist in 2017 IROS, and the TJ Tarn best paper in robotics in 2018 Robio. And his current research interests include robotic manipulation, vision-based control, micro-nano robots, and human-robot interaction. So thanks, Xiang, for being here, and the floor is yours.
Okay, thanks for the great introduction.
I think, David, you need to stop sharing screen so Xiang can start sharing it.
Yeah.
But still, David is sharing the slide, so.
Sorry, I was about to go to the toilet, imagine. Okay, share new. Stop sharing. Yes, my bad. Okay. Xiang, my man, the floor is yours.
Okay, perfect.
Okay, okay, thanks for the great workshop. So I'm very happy to be here to present some of my recent works. So, okay, so my name is Xiang Li from Tsinghua. So the title of my presentation today is the adaptive control for robotic manipulation of a deformable linear object. Yeah, the title is seems a bit long, but actually mainly covers three topics. The first topic is offline learning together with the online learning. So the second topic I'm going to say is the robotic manipulation of multiple features. And the last topic, we will discuss some application to the 3D robot. So here is some robotic manipulation of a deformable object in the literature. So actually, this result. The result on the bottom, the left one is the result from my previous group, both for Hui Liu's group. So we can see that in the presence of the change of the significant mass of the deformable object, we still can manipulate this green feature point to the desired position. So in our work, we consider this formulation. So this is a deformable linear object. So both ends of the deformable linear object are grasped by manipulator. There are two manipulators. So this is the feature point. The feature point marked with the red color. So then based on this formulation, we can have this equation. So y dot means the feature velocity. The r dot is the end effector velocity, which is also the control input. So these velocities are related by the Jacobi matrix. And we assume this Jacobi matrix will depend on the shape of this deformable linear object. Actually, this shape in the representation, we will use multiple features to represent the shape. But the problem is that in most cases, when we manipulate the deformable linear object, we have no idea about the deformation model. So in the presence of the deformation model, so this Jacobi matrix is also unknown. So the problem becomes, how can we manipulate the wires, the ropes in the presence of unknown Jacobi matrix? So according to our survey, so there are two ways. So first is a model-based method. But this method is relatively computationally involved, and also it requires the structural information of the deformation model. The second method is the data-driven method. Now the data-driven method become more and more popular in these publications. So we further can divide the data-driven method into two ways. For the offline method, the quality of this estimation of Jacobi will be limited by the quality of the data set. For the online adaptation for the Jacobi matrix, actually it is locally effective, which means that the design shape cannot be far away from the current shape. And also, if let's say if the deformable linear object is now at the same configuration in the task space, but still we have to redo the estimation for the Jacobi matrix. So this is our formulation. Actually, in this work, we want to combine the advantages of the offline learning and the online learning. So in the offline learning, we do the offline learning first. So the offline learning, we just move the robot manufacturer in a random manner. So this offline learning is to provide a good initial value for the online adaptation. And the online learning will further compensate the offline learning. So this is to combine advantages of this two estimation method. So our novelty here in this work is that we can claim we can directly transfer the result obtained in the offline phase to the online phase. So there's no need to do any additional work for the formatting. We can directly transfer the result. So we believe such way can fully explore the advantages of these two methods. So this is a bit straightforward for the offline learning. So basically we use the fully connected neural network. So the input is the feature position. We have multiple features, m features. So this x1 to xm represent the feature position. So the middle layer, we use a series of nonlinear functions. We can choose RBF for the radial basis function. It's a very standard. And the output will be the column of the Jacobi matrix. So we would like to point out that actually this structure can be used for the estimation of all the features the Jacobi matrix, because for multiple features, for all these multiple features, they all receive, for the Jacobi matrix, they all receive the feature position. So we can use same structure, just a one structure to estimate all the Jacobi matrix for the multiple feature along the deformable linear object. And this is our loss function for the supervised learning. So basically we use the EW, which is the difference between the sensory feedback. We can use the, let's say, sensor or vision to measure the white dot. Then this is the difference between the measurement and also the estimation in the last round. So this is some result for the offline approximation. So the first three figures represent the estimation for the Jacobi matrix, and the red one represent the ground truth because it's a simulation. We use the simulation to validate the offline estimation first. So this is the ground truth. So we have the blue line for the training for 5 minutes. Then we have the green one for the training for 61 hours. Actually, definitely we have a green line performs better than blue line. But in the actual implementation, we may use the blue line. We may just do the offline training for 5 minutes because we have the online phase. So further in the online phase, we will further compensate the modeling errors. So the first three figures represent the estimation for the Jacobi. This is a Jacobi. And also we can use the similar structure for the estimation of the pseudo inverse of the Jacobi matrix as well. Also we have 5 minutes and 60 minutes. We can simply use 5 minutes, then we move to the online phase. So this is our online phase controller. So this is the estimated Jacobi matrix. So this Jacobi matrix will start from the result obtained in the offline phase, and then we keep updating it with the feedback error in the online phase. So this is the control input. So this delta Y represent the position error, which is the feature's position minus the design position. So this is our online adaptation law. So we can see that y dot is the rate of the change of the weight of the neural network. So this update will start from the initial value of the result in the offline phase. So this is why we point that we can directly transfer the result obtained in the offline phase, because the weight of the neural network in the online phase will start from the initial value, which has been estimated by the end of the offline phase. So then this way we'll start from this good initialization value, and then driven by the delta y and the approximation error, modeling error at the same time. So let's say if the point is not at the desired position, this delta y is non-zero. So this w hat dot is non-zero. So the online adaptation continues. So only when the delta y and the EW goes to zero, this w hat dot equals to zero, because the feature has been manipulated to the desired position. So there's no need to do the online adaptation, because we have realized our control works. So we have some comparative studies for the online adaptation. So this is the feature, and the red one represents the target point, which is the pick one point from the multiple features and manipulate the feature to the desired position. So this is the desired position represented by the green point. So we design the online controller to move the the status of the y to the final status. So the below figure shows the result. We can see that firstly, if we deactivate the online adaptation, so we can still have the position error converge to zero in steady state. But if we can add the online adaptation, we can see that the error can reduce to zero in a faster speed. So this also shows the effectiveness of this online adaptation. So this is some simulation and experimental result. For the simulation, if we can specify different, trajectory or combination of some set point for the features, we can actually specify different tasks for the shape control of the deformable linear object, but it's basically the planning works. So the below two video actually shows the comparison between the online adaptation. So the first result, we don't use the online adaptation. We simply use the Jacobi matrix obtained in the offline phase. So we can see that in a steady state, we cannot have a very exact information about the Jacobi matrix. So in a steady state, we cannot move the feature to the desired position. But then if we can add the online adaptation, so first the convergence of the position error is faster compared to the case that there's no online adaptation. And also in a steady state, we can successfully manipulate all the features to the desired position. So the next topic is about the multiple features manipulation. Actually, the previous slide has shown some result for the robotic manipulation of multiple features. We find actually there are several challenges for the manipulation of multiple features. The first challenge is that we cannot always ensure the controllability of the system, because let's say if we manipulate multiple features, the control input may be less than the control output. So maybe the system is not controllable. The second challenge is that in some cases, during the transient stage, if we manipulate multiple features at the same time, maybe there's some conflict between multiple features. And the last challenge is the same as the previous one. We have to deal with the Arnold deformation model, which is also the Arnold Jacobi matrix. So we have this dynamic region control to deal with these aforementioned three problems. So the first, we can see that these are three features So for each feature, we formulate a very big region. So at the beginning, all the features are inside the region at the beginning. So the center of this region is the reference position. You can consider as the design position of the feature. Then we shrink the region. We scale down the size of the region one by one. So when the region shrink or reduce to a point, this feature also manipulate to the design position. And if all the features are around the design position, we can realize the design shape. The advantage, the novelty by doing this is that firstly, we just manipulate one feature at one time, so we can ensure that the control input may not be less than output, so the controllability problem may be addressed. The other advantage is that actually when the features is inside the region, there is no control input. So when one feature is being manipulated, other features just moving accordingly. So we can address the conflict between multiple features. Later we can show the result. So these are more detail for the region control. So this T bar represent the transformation matrix. So we can specify the transformation matrix to move the size of the region reduced to a very small bound to determine the design shape. This is realized by specifying the potential energy function. So this design region corresponds to the bottom part. So when the region shrink, the potential energy, the gradient of the potential area will just push the feature to the center of this bottom part of the potential energy. So this is a simple comparison. We can see that if we manipulate multiple features at the beginning, so this the second point will move downward and the sub point will move. Sorry, the second point is moving upward, the sub point is moving downward. So there's a conflict between these 2 points. So later we use the region control for the 3 multiple points. So this is the first region. So when the first point is being manipulated, so these 2 regions remain static. So actually in a steady state, you can see that the second and third point are away from their design positions, but it's okay. It's just the transient stage. So when the second region reduce to a very small bound, this will just push the feature back to the design position, and also for the last feature. So these are 2 technical we mentioned before. First, we have to set the gradient of the potential energy is very steep. So once the feature is around the boundary of the region, this is a very steep gradient which has to push the feature back to the design region. And also, if let's say if the feature really escape the design region, so actually we can make the region bigger again. It's dynamic region to recapture the feature and then rescale down the size of the region. These are more illustration. So this result, the first video shows that we can manually pull the feature outside the design region to mimic the scenario where the feature escapes from the design region. So the region becomes bigger to re-enclose the feature. So by using some planning technique, we can specify we can match the specific task for the shape control of the deformable linear object. And also we can choose some maybe more critical features and additional features to make relatively complex the shape. This is circular shape. We can make the circular shape match with the pole under the circular shape. The last topic is about the applications. We actually have a project working on the 3C robot. 3C robot is to deal with some deformable object in the 3C manufacturing, such as the flexible PCB or the USB wires. Due to the deformation, most of these deformable objects in the 3C manufacturing are done by humans now. But actually, the market for the manufacturing is very big. So we get this data just for the iPhone charger cable, the USB data cable. Just for the 3 months, the sale of this charging cable is 76 million. It's 76 million. So it's really a very big global market. So these are solutions. So this machine cannot deal with the deformable object, can just solder the standard, the rigid PCB. So this is the latest, the state of the art for the USB soldering. Still, we can see that it's not fully autonomous. So we summarize some limitation why we cannot apply the existing result to the 3C manufacturing. First, we have to assume that the robot manufacturer is always controlled to contact the deformable object. The second limitation or assumption is that we actually mainly consider the kinematic level. But in the 3C manufacturing, the speed is very high. So we have to design our controller with the consideration of the robot dynamics. So, so in this project, we propose some prototype for the 3C robot. Sorry, how long do I have? How many minutes? Okay,
You have
yeah.
some other few minutes.
Okay.
Please, maximum 5 minutes.
Okay.
Thanks.
Yeah.
Thanks.
Yeah. Okay, so first, the deformable object we are going to consider is the flexible PCB. So this is the system. So we have the vision is 2D vision to capture the feature, and then we use the vision feedback to control the robot to contact the flexible PCBs and do the active deformation. The main challenge here is that actually this contact point is away from the feature, is the solder pad. So let's say if the PCB is not calibrated, the deformation model is unknown. So we have no idea what is the exact information of the Jacobi. So similarly, we use the adaptive neural network online to deal with the unknown Jacobi. And the other contribution for this work, we can combine different feedback information based on the regional feedback into a single controller. There's no hard switching between different phases. So first is the region control for the contact test. This controller is to drive the robot manufacturer to automatically contact the flexible PCB. The reason we use the region is that the region can provide more flexibility for the contact task, because what we need to do is just move the robot to contact the deformable object. So there's no need to specify a very fixed, very specific contact point. So another controller is this vision-based controller. So the key point for the vision-based controller is that we have to ensure that the robot has already contacted the flexible PCB. So definitely, if there's no physical contact, there's no way to do the active deformation. So this composite vector is to synchronize the contact task and the active deformation. So sorry, due to the time constraint, I cannot say too many details. Later, if you want to discuss, yeah, we can discuss later. So this is a prototype for the flexible PCB, and this is some illustration for the contact and active deformation. And this one shows that if we can make the two solder pad match, then we can activate the soldering machine to solder them together. People may ask, how do you set the design position for the feature? So in this experiment, we just show the idea of the contact and active deformation. So we manually specify, but in actual implementation in a factory, we can use some visual tracking algorithm to check the solder pad of the other PCBs in real scenarios. So this formulation can also be used for the shape control of other robotic systems. So this to show that if we start from different initial position, we can still move the feature to the desired position. So the last object we are going to discuss is the USB-Y. So as we mentioned before, people need to get involved at the beginning. So what the people need to do is to separate the 4 USB-Ys and then make sure that the color of these 4 USB-Y is correct. is the design sequence. This is very important. If the color sequence is not correct, even we can manipulate the 4 USB wire. This soldered or assembled USB cable cannot function properly at all. So we propose this another objective for the robot. So combine 2 levels to try to push the robot to automatically transit between different phases of the manipulation to automatically grasp the wire and manipulate wire to the desired position. So this is another solution for the USB soldering. So we have a more hardware design. So the robot can automatically separate the 4 wires and then just sort the wire, make sure that the color sequence is correct, and finally press the wire. And through the result, we can see that there's no human involvement at all. It's fully autonomous. So this is principle for the separation and the sorting module, just skip. And in the actual implementation, we also use some deep learning, deep vision network. This is to ensure that the detection of the grasping point is correct, even in the change of the illumination or in a change of the factual environment. So finally, is the conclusion for my talk. So first, we propose the offline learning and the online learning. So we want to combine the advantages between these 2 phases, but the problem is that how to transfer the result directly to the online phase. So we propose some technical based on the neural network to realize this objective. The second topic is the dynamic region. So for the multiple features, so we believe by using the dynamic regions, we can address the conflict between multiple features, and also we can ensure that the system may be controllable for multiple features. So last topic, we did some application to the 3C manufacturing, and we built a prototype, and with the regional feedback, we can improve the autonomous capability for the robot. So this will be the end of my presentation. Thank you so much for it. Sorry for the delay. No.
Okay, thanks for the talk. It was really nice, and I think you showed a really nice combination of the formalism from control theory and the learning. There is a question. The Adrian Kessler is asking on slide 11 how to ensure that the sequential approach of servoing one feature after another is successful. And is there a case where trying to servo the 3rd feature will put the 1st feature out of its target? For instance, some cable with a higher bending stiffness.
Yes, very good question. Actually, we are working on it. My answer to this question is that actually we don't need strictly assume that just the one feature is being manipulated at one time. The reason we introduce the dynamic region is try to make the controller maybe as sparse as possible. So definitely, if one feature escape from the region during the manipulation, this will generate a control input. But we can use the region control to make sure that not all the features will escape from the dynamic region. So if let's say the feature is outside the dynamic region, still the region controller will try to push the feature back to the region. But definitely by using the region control, we can control less dimension of the state compared with you just activate the control for multiple features, all the features at the same time.
Okay, thanks. We have another question from Zhu Pang, and the question is if there is any way to predict whether the target points or shapes configuration is achievable or not, since every time if we need to execute to check that the process will be very time consuming.
Yes, actually it's also very, very good question. And in fact we are also working on it. I do not have an exact answer to this question, but maybe I have some suggestions. What we need to do is that, let's say if you manipulate the deformable linear object. And definitely, when you specify the design position, we have to ensure that it's achievable. First guideline for specifying the design position is that you have to match the task, right? You have to match the task. You have to match the main features of that task. This is the first guideline. The second one is that we have to consider, let's say, the constraint of multiple features. So when we specify a series of design set points for the multiple features, we have to ensure that this distance between two neighboring features is can match the feature you specify along the deformable linear object. This is the second guideline. The third guideline we are working on is that we also taking part into the dynamic model, the deformation model or dynamic model of this deformable linear object. So for some cases, maybe it's a bit elastic. So some distance between the initial distance of two features can be enlarged or can be maybe, I have no idea, maybe condensed a bit at a steady state. Yes, so this, yeah, I hope this can provide some suggestion for your future work. Still, yeah, sorry for that. We're still working on this topic.
Okay, nice, thanks. And I have just a curiosity. So regarding the multi-features application, so one question is, are these features pre-selected, right? And in this case, is there a kind of procedure on how to select these features and if they then affect the performance of the approach?
Yeah, it's a good question. But I think for selection of the feature, Debbie have give a very great workshop. I think we can refer to the feature selection based on his talks. For my experience, if we're talking about application, so for the 3C manufacturing, we just choose the feature, let's say case by case. If we are going to solder the USB wire, definitely the feature will be soldered back on the flex or PCB. If we are going to deal with the sorting task of the USB cable, there are 4 USB wires. So the feature will be 4 different colors, I mean USB wires. So it's, I think in practical, it's a totally case by case. Yes.
Okay. Thanks a lot.